Earth's toughest microbes could help humans live on Mars. Think about that for a moment. Ever since humans first set foot on the moon, we've been asking ourselves one question. What's next? Space agencies around the world have treated the idea of living beyond Earth as the major long-term goal. And of all the destinations we can realistically reach, Mars stands out as the undisputed leading candidate. Its dramatic terrain, those few hauntingly familiar traits, they make it feel like humanity's next frontier for exploration and settlement. But here's what most people don't realize. Building a lasting human presence there remains one of our biggest ambitions, and simultaneously one of the hardest problems science and engineering have ever faced. Now, here's something that might surprise you. Mars wasn't always the frozen wasteland it is today. Over billions of years, the planet lost the thick atmosphere that once helped protect its surface. What remains? An environment that looks absolutely nothing like what most Earth life can tolerate. The air is extremely thin and mostly carbon dioxide. The atmospheric pressure, less than 1% of Earth's, and the temperatures, they swing wildly from about -90 degrees Celsius. That's a bone-chilling -130 Fahrenheit, all the way up to 26 degrees Celsius, or 79 Fahrenheit. But wait, it gets worse. There's constant cosmic radiation bombarding the surface. No breathable air whatsoever. Zero. That means a Mars shelter has to do far more than just provide a roof and walls. It must function as a life-supporting refuge that can withstand a world that is literally, physically built to break down living systems. This is survival on hard mode. So here's the massive challenge we're facing. Shipping large amounts of construction material from Earth. It would be far too expensive and completely, utterly unrealistic. We're talking astronomical costs that would make any Mars mission impossible. We need a practical approach. We need to think differently. We need to build with what's already on Mars. This is where ISRU comes in situ resource utilization. In simple terms, using local materials, and it's absolutely central, fundamentally essential to any plan for sustainable human life on the red planet. The mind-blowing question now, here's where things get really fascinating. NASA's Perseverance rover has been collecting samples from Jezero Crater, an ancient Martian riverbed, and these samples, they may contain evidence of very early life, actual Martian life. That possibility raises a bigger, more profound question that goes beyond just searching for past biology. If microbes once lived on Mars, could microbial processes also help us build there? Could the answer to colonizing Mars be hiding in the smallest forms of life? Think about that for a moment. Really think about it. Life on Earth began with simple microorganisms in shallow water environments. These weren't complex creatures, just tiny, simple cells. Over time, these tiny organisms reshaped our entire planet in absolutely enormous ways. They helped fill the atmosphere with oxygen, making complex life possible. They created structures as durable as coral reefs, some of which have stood for thousands of years. As we look toward Mars, researchers are asking whether small life forms could again play an outsized role, this time by helping turn a barren, hostile world into a place humans can actually survive. Could history repeat itself on another planet? Our research takes inspiration from these natural systems and brings together experts from multiple fields in an international cross-disciplinary effort. We're talking astrobiologists, geochemists, material scientists, construction engineers, and robotics experts all working together. The focus? Biomineralization. This is a fascinating process where microorganisms, bacteria, fungi, and microalgae create minerals as part of their normal metabolism. It's what they do. Biomineralization has influenced Earth's landscapes for billions of years, shaping our world in ways most people never even think about. And microorganisms that thrive in harsh settings like acidic lakes, volcanic soils, and deep caves. They may be especially useful as we explore what could work under Martian conditions, and they might just be our secret weapon. Using rover data about Martian soil, what we call regolith, our team is examining different microbial mineralization routes to see which ones can produce strong materials for habitats, while avoiding interplanetary pollution risks, and the most promising option so far, something called
biocementation.
In this approach, microorganisms produce cement-like substances such as calcium carbonate at room temperature. No massive industrial equipment needed. No complex machinery. No enormous energy requirements. Just life doing what it does best. Building a key part of the work centers on a partnership between two bacteria. And this is where it gets really interesting. Almost like science fiction, but completely real. One is Sporus arsina pastori, which is already known for creating calcium carbonate through a process called ureolysis. The other is Crucochidiopsis, an incredibly tough cyanobacterium that can survive extreme environments, including simulated Martian conditions. We're talking about a microbe that laughs in the face of conditions that would instantly kill most life together. They function as a cooperative system, like the ultimate construction partnership. Crucochidiopsis releases oxygen, helping create a more supportive microenvironment for Sporus arsina pastori. It also produces an extracellular polymeric substance that can actually protect Sporus arsina pastori from damaging UV radiation on the Martian surface. It's like a microscopic shield. In return, Sporus arsina secretes natural polymers that support mineral formation and help bind regolith together. The result? Loose Martian soil can be transformed into a solid, concrete-like material. It's like they're working as a construction team at the microscopic level. Nature's own builders. The long-term vision is to combine this bacterial co-culture with Martian regolith and use it as feedstock for 3D printing on Mars. Just imagine that for a second. Robots printing buildings using living organisms and Martian soil. This concept sits at the meeting point of astrobiology, geochemistry, material science, construction engineering, and robotics. It's where all these fields collide. If it works at scale, it could completely change how structures are designed and manufactured for the red planet. We're talking about a revolution in space construction. But here's the kicker. The potential value isn't limited to just construction. Not even close, because Crucochidiopsis can produce oxygen. It could contribute to both habitat stability and astronaut life support. We're talking about building materials that literally help you breathe. Over longer periods, ammonia created as a metabolic byproduct of Sporus arsina pastori could help enable closed-loop agricultural systems, growing food on Mars, and it might even play a role in Mars's terraforming efforts down the line. We're not just talking about building shelters, we're talking about making Mars livable down. Even with these incredibly promising ideas, the work is still at an early stage. International agencies are aiming to build the first human habitat on Mars in the 2040s. But it's not. Here's the problem. Recurring delays in Mars sample. Return missions limit how quickly Mars-specific construction methods can be tested and confirmed. We're working somewhat in the dark. With space agencies planning crewed missions in the coming decade, yes, the 2030s research on bio-derived construction needs to move forward. Now, to be ready when humans arrive, the clock is ticking. From an astrobiology standpoint, a major task is understanding how these microbial communities behave in actual Martian regolith and how they endure the planet's many stresses. Temperature extremes, radiation, low pressure. It's a brutal environment. Regolith simulants in laboratories provide a practical way to test co-cultures in Mars-like conditions and to build models that predict how well bio will perform when we finally get there. Every test brings us closer to the real thing. Robotics adds another fascinating layer of challenge. It's difficult, almost impossible really, to reproduce Martian gravity on Earth, yet gravity affects 3D printing and autonomous construction in significant, fundamental ways to prepare for future missions. We need strong control algorithms and specialized protocols that let robotic systems build efficiently and reliably in Mars's unusual environment. We're essentially teaching robots to build in conditions they've never experienced. Progress may be incremental, step by step, test by test. Every experiment, every successful test, every refined procedure, they all move us closer to a future where humans can truly call Mars home. And maybe, just maybe, the key to building our future on another planet lies in the smallest forms of life we know. The microscopic builders that once transformed Earth might just transform Mars too. The question isn't if we'll live on Mars, it's when, and these tiny microbes might be the ones that make it possible. Welcome to the future of space construction. Welcome to the microbial revolution. Let's learn science and technology together. You can watch my other videos from the link in the upper right corner.